In the previous video, we came up with an expression for the electric potential energy for a pair of point charges. And now I'd like to extend that to include cases where there are more than two charges, like for instance this 5-charge system here. So the idea is we'll be extending our result with two charges by thinking conceptually about moving the charges in from infinity one at a time. So although I've drawn the final destinations here, at the moment we imagine all the charges are sitting out at infinity, and then the very first charge I bring in will be this charge number 1 coming in from infinity. Well, if it's just that charge all by itself, the other charges are still infinitely far away. So the potential energy of the system, when I just have Q1 sitting here, is going to be, go ahead and pause the video and take a guess. Yeah, 0, because everything is still infinitely far away. Now, when I bring in the second charge from infinity, well, this is exactly what we handled before. And at that time, we got that the potential energy of the system now, so what I add to this, I will add to the potential energy 1 over 4 pi epsilon naught Q1 Q2 over this distance right here. And so now we've got to be really careful when we think about our distances. What's probably going to be the best thing to do is just go ahead and mark our origin somewhere. So this is my origin. And then we will just denote the position vector R1 here. And then this would be the position vector to this charge here, R2. Let's try that again. There we go. And similarly, R3, R4, and R5. So thinking back to the days of displacement, this vector minus this vector is just the vector that takes you from here straight to there. So if we just take the magnitude of it, we'll say that the distance between these two charges is my vector R1 minus my vector R2, and take the magnitude. So it doesn't matter if it's R1 minus R2 or R2 minus R1, we just want the magnitude of that vector. So this is what adding a second charge brings to the game. Now if I bring in a third charge, what is that going to bring into the game? Well, when I bring in charge number 3 from infinity, like so, oops, charge number 3, we don't have to worry about how Q1 and Q2 are interacting. We already took care of that with our expression for U2. So this will be, now we will apply superposition and first pretend that Q1 and Q3 are the only two charges in the universe. So we'll just temporarily ignore this one and say, oh, okay, this is going to be 1 over 4 pi epsilon naught. Let's just open a bracket here. This potential energy of this pair of charges will be Q1, Q3 over R1 minus R3. And then what we'll do is we will instead say that the only two charges in the universe are Q2 and Q3, ignoring Q1. So applying superposition, the contribution from the interaction between these two charges will be Q2, Q3 over R2 minus R3. And again, we're just taking the magnitude. Alrighty, whoops. And we can wash, rinse, and repeat. Sorry about that. We can wash, rinse, and repeat for charge 4 and charge 5. Let's just go ahead and write down what those expressions would look like. So U4 would be 1 over 4 pi epsilon naught. And so this would be Q1, Q4 over R1 minus R4 in absolute value plus Q2, Q4 over R2 minus R4. Take the magnitude plus Q3, Q4 over R3 minus R4. Then finally plus, oh, sorry, that's it. And then take the magnitude. There we go. Then finally U5. That would be 1 over 4 pi epsilon naught. And I won't write the whole thing, but Q1, Q5 over R1 minus R5. Take the magnitude plus and such until we end up with Q4, Q5 over R4 minus R5. Take the magnitude. Okay, that looks like a mess. And so then the total electric potential energy will just be the sum of all of those. So this will be U1, which was 0, plus U2, plus U3, plus U4, plus U5. If we go take a look at this, this will be 0. Everybody's got 1 over 4 pi epsilon naught. And then what you see is that we've got every possible pair of charges occurring once. 1 and 2, 1 and 3, 2 and 3, 1 and 4, 2 and 4, 3 and 4, 1 and 5, 2 and 5, 3 and 5, and 4 and 5. So there is a way to write this more concisely using summation notation. So we can say that if we have n charges, so this is the general case. If we have n charges, it'll be 1 over 4 pi epsilon naught times the sum as j equals 1 to n. So that's the number of charges. Sum as for I less than j, qi, qj over the magnitude of ri minus rj. And so the way this is going to work, just if you haven't seen this kind of a summation notation before, let's just step through it for this example real quick so that we see how it works. So the first thing you do is you'd make j 1. So you then say, okay, we start running we start counting all the i's that are less than j. Oh, oops, there aren't any. So that corresponds to our U1 equals 0 up here. All right, next iteration. J is now 2. So I can be anything that's less than 2. Well, literally the only choice left is 1. So this becomes Q1, Q2 over R1 minus R2. So that was the U2 that we found right here. Then we go ahead and make J 3. So now that J is 3, I can be 1 or 2. So we will have a Q1, Q3 over R1 minus R3 and a Q2, Q3 over R1 minus R2 minus R3. Then J would be 4 and I would be 1, 2, and 3. So it'll give us a Q1, Q4, Q2, Q4, Q3, Q4, just like we got here. And then finally, when J is 5, I can be 1, 2, 3, or 4. So this would be Q1, Q5, Q2, Q5, Q3, Q5, and Q4, Q5, just like we got there. If you've had some computer programming in your experience, another way to think about this is like this. If you haven't had any computer programming, don't worry about it. But this is just to as a way of explaining in case you do know. This would be equivalent to the following stub of C. You would write something like for j equals 1, j less than or equal to n plus plus j. For I equals 1, I less than or equal to j plus plus I. And then you would say u plus equals the stuff. And then close your braces. So if you've had some computer programming, this is what this looks like. Yes, I know you should initialize it, but just trying to get some sense of what it's like. It's like a nested for loop, if you've seen that kind of a thing before. If you haven't had any computer programming, don't worry. Just work through this until you match this example, and then it'll make some sense. All right. And again here, let's go ahead and do a more concrete example. So this is going to correspond to a situation that isn't terribly realistic, so the energy is actually going to be quite high. But let's say we have a system of 4 charges. So we'll have plus 1 microcoulomb here, plus 2 microcoulombs here, plus 1 microcoulomb here, and then finally Q4 over here at plus 2 microcoulombs. Let's say the whole shooting match is sitting on a circle with a radius of 1 millimeter. Okay, so the idea is going to be we need to add up the potential energies from literally all of our possible pairs. So we can say that U here would be equal to, well, one of our pairs would be 1 and 2. Then we would have 1 and 3 and 1 and 4. 1 and 4. And then we would add in, starting from 2, we would have 2 and 3, 2 and 4, and finally 3 and 4. And we only want to count each pair once, and so that turns out to be it. There are a grand total of 6 pairs. Now, when we get to writing these, we notice that we can simplify our life a little bit if we notice that these 4 pairs here are all going to be the same. You'll have 1 microcoulomb charge and 1 2 microcoulomb charge. And this distance here is a millimeter. That distance there is a millimeter. I'll make that distance there 2 millimeters. So first off, we can just say U12 is going to equal U23, is going to equal U34, is going to equal U14. So I'm just going to put checks next to those. Those are all equal. So that makes our life a little easier. And we can write this as this is 4U12, just again recognizing the equality of those 4, plus U13 and U24. And even here, if you wanted to be really clever with it, here the separations, let's do this in a different color. In both cases here, the separations are between the charges are going to be 2 millimeters. And the only difference is that each of these charges is doubled. And since the potential energy goes as K, Q, QA, QB over R, if I double each of these charges, I quadruple this. So we can observe that U24 is 4 times U13. So the cleanest I can get this down to is 4 times U12 plus 5 times U13. But at least that gets us down to just 2 signs. So this will be 4 times K Q1, Q2 over R12 plus 5 times K Q1, Q3 over R13. So we can pull out a K, and then we can just go and, so 4 Q1, Q2 over R12 plus 5 Q1, Q3 over R13. All right, that's really as far as we can take it without substituting in numbers, so let's go ahead and do that. So this will be 9 times 10 to the 9 Newton meters squared per Coulomb squared, times 4 times, this was 1 microcoulomb, so 1 times 10 to the minus 6 coulombs, 2 times 10 to the minus 6 coulombs over the square root of 2 millimeters, so it'll be root 2 times 10 to the minus 3 meters, plus 5 times 1 times 10 to the minus 6 coulombs times the same thing again, so squared, over 2 times 10 to the minus 3 meters. Grind it through on your calculator, you'll get 73.3 joules, which is an awful lot of energy for a small system like that, but that should just give you some idea of how large the electric force is. So we'll wind this video down by taking a look at what happens if you have a dipole in an electric field. Oops. All right. Boy, that was a really good in there, wasn't it? There we go. So we imagine you've got some sort of electric dipole here. So one end will be minus, the other end will be plus. And associated with it is a dipole moment P. And we'll go ahead and say that our dipole is sitting in a uniform electric field E. And so we can say that our dipole is making an angle, dipole moment is making an angle phi with respect to the electric field. Now we'd already seen that the torque on dipole is going to be P cross E. So if I just want to work in magnitude, that's going to be PE sine phi, but we got to be a little careful here. I'm going to need a minus sign here because this is a restoring torque. If we're rotated counterclockwise, the torque is clockwise. If we're rotated clockwise, the torque is counterclockwise, so I need the minus sign to reflect that. So just like we can say that the work done by a force is the force dot with the displacement, you can do exactly the same kind of thing with torques. So we can say that a differential of work done by the electric field on the dipole will be the torque it exerts times the differential of angle you rotate through. So this will be minus PE sine phi d phi. So then the work done by the electric field will be minus PE, integrate from phi initial to phi final, d phi sine phi. Now, before we do this, we also remember that the change in the potential energy, the change in the electric potential energy will be the negative of the work done by it. So we then get to drop that minus sign, and we are left with PE integral phi initial to phi final d phi sine phi. And the integral of sine is minus the cosine. So we will get minus PE cosine phi evaluated from phi initial to phi final. Now, if I want to choose a potential energy function, once again, I am free to do it to within an additive constant, but it'll probably just make the most sense to make the choice that the potential energy, so we're just setting it to be this, the potential energy for a dipole as a function of angle will just be minus PE cosine phi. And then to get the difference, I just take the difference and I'm good. But if I write it this way without any potential additive constant, which I would be allowed to do but isn't really useful, this allows me to notice that this is P dot E, so I can just write that this is minus P dot E. Okay. So I mentioned earlier that if we place a dipole in an electric field and disturb it a little bit, that would undergo harmonic motion. We can start to see that a little more clearly. So say if I plot the potential energy as a function of phi, it's a negative cosine wave, right? It's going to look something, oh, that's awful. It's going to look something like that. Well, this is a cosine wave. And you know it is because I said it was. I labeled it. So this will be pi. This will be minus pi. This is 0 here. So with our choice of the potential energy being minus P dot E, this means that its lowest value, it'll be minus PE, and its highest value will be plus PE. And then as long as I don't give it too much rotational kinetic energy, let's say we do something like make the total mechanical energy this much, then this will be our turning points here. And our dipole will be executing harmonic motion between whatever these angles are here. Alrighty. Catch you in the next one.